Good morning to you all. My name is Laura. This is kind of my first conference, so I'm a little bit nervous. I hope not to spit too much. So in this presentation that is entitled Can Cencov meet Petz? I would like to share with you some of the ideas that I have been developing for my first year as a PhD student, together with the researchers Florio Ciaglia, Fabio Di Cosmo, and the professors Alberto Ibort and Giuseppe Marmo. So this presentation will be divided into two main parts. In the first part, I will briefly recall the pillars of classical and quantum information, namely Cencov and Petz problems, so maybe I will bore you a little bit in this part. And in the second part, I will briefly introduce the framework of double-star algebras, and I will present you a unified mathematical picture for quantum and classical information geometry in finite dimensions that encompasses and unifies Cencov and Petz problems. So let's start with the first part. So if we have a measurable space with a given sigma algebra, we can form the set of all probability measures over this set. So this set can be endowed with a topological structure, but it cannot be endowed with a smooth manifold structure. However, we can study this set from a differential perspective point of view, differential geometric perspective point of view, if we introduce the notion of a parametric model. So a parametric model is nothing more than a collection of probability measures or probability distributions, opportunely parametrized by the points of a smooth manifold that is called the parameter space, okay? So the parametrization is given by this immersion map that assigns to each point in our smooth manifold a probability distribution that in the vast majority of applied situations can be written as a dominated probability measure. So a parametric model that maybe is familiar to you is the parametric model of quotients, where in this case, the immersion map assigns to each point in our smooth manifold, which is this Cartesian product over here, a normal probability measure over the real line, okay? So now, if we have a parametric model, this is a triple like this, since M is a smooth manifold, we can endow it with a Riemannian metric structure. So one Riemannian metric structure that actually emanates from the very construction of parametric models is the Fisher-Rao metric tensor. And if we have some local coordinates on our manifold M, the local expression for this Riemannian metric tensor can be represented by an n times n matrix whose entries are given by this expression over here, from which we can already see that the Fisher-Rao metric tensor is actually strongly related with the set of all probability measures over the selected measurable space, okay? So in fact, if we take back the example of quotients, we can see that the Fisher-Rao metric tensor that can be explicitly calculated in this case is related with the parameters of our normal probability measures, okay? So now, in order to, in pursuit of discussing Cencov theorem, I would like to introduce a specific parametric model. And for that, we're going to consider a finite and discrete set, which of course can be endowed with a measurable structure. So in this case, it can be proved that the set of all probability measures over this finite set or discrete set is actually isomorphic to the n simplex in our n+1. Okay, so this n simplex is not a smooth manifold, but it has an open interior which can be endowed with a smooth manifold structure. And therefore, we can consider the following parametric model, where now the immersion map is given just by the canonical inclusion of the smooth manifold delta n into the n simplex. So this parametric model is Cencov parametric model, and it is in somehow the environment where Cencov theorem actually lives, okay? So now that we have this smooth manifold structure, we can endow it or address it with a Riemannian metric structure. So in principle, this metric could be anyone, but we would like to consider only those Riemannian metric tensors that are invariant under a special kind of linear maps, preserving probabilities, which are called congruent embeddings. And the problem we would like to address is to find all families of Riemannian metric tensors on the manifold delta n, satisfying this invariance property, which is a pullback, okay, of this Riemannian metric tensor for all congruent embeddings. So this problem was actually posed and solved by Cencov, and it is the content of his classification theorem, which roughly speaking states that among all Riemannian metric tensors that can be, let's say, defined on the open interior of the finite dimensionals and simplex, the Fisher-Rao metric tensor is the unique up to a constant, which is greater than 0, Riemannian metric tensor that is invariant under all under all congruent embeddings. Very good. So now that we have this classical result, this uniqueness result, I would like to pass into the quantum case, where of course the question would be if this uniqueness can be extended in somehow to the quantum domain. So the quantum case proceeds mainly by analogy. Therefore, if in the classical case we have a finite and discrete measurable set, in the quantum case we will have a finite dimensional Hilbert space. And the set of all probability measures over this set will be, let's say, translated into the set of quantum states. So as in the classical case, this set is not a smooth manifold, but it has an open interior, which is given by the set of all faithful quantum states, which can be endowed with a smooth manifold structure and therefore can be considered as the quantum counterpart of the manifold delta n. So now that we have this smooth manifold structure also in the quantum case, the idea would be to pose a Cencov-like problem. And therefore, the first ingredient we are going to need, based on the classical case, are the maps from which, in the classical case, we ask for invariance. So in the classical case, these maps preserve probability and strictly positive probability vectors. And therefore, in the quantum case, we would like these maps to preserve states and faithful quantum states. So therefore, we are going to propose that these maps to be faithful and completely positive trace preserving maps. But just as a remark in here, take into account that these maps are not the exact quantum analog of a congruent embedding, because in this case, we are not asking for these maps to have a left inverse, which is also a faithful DP map. So now, the quantum counterpart of Cencov problem, which was actually raised by Cencov and Elena Morozova, was to find all families of Riemannian metric tensors now on the manifold of faithful quantum states over an arbitrary Hilbert space, satisfying this monotone invariance condition for all faithful CP-TP map. So one of the things that we can immediately note from here is that we are not asking for the equality of the Riemannian metric tensors, but what can be proved, which is very important, is by applying double monotonicity if you want, is that all Riemannian metric tensors that are monotone invariant are indeed invariant under all quantum congruent embeddings. Okay. So this problem was actually solved by Petz, who stated that in contrast with the classical case, in the quantum case there exists a family of Riemannian metric tensors on here, satisfying the monotone invariance property, and the expression of these Riemannian metric tensors is given in terms of a superoperator that must depend on an operator monotone function satisfying this extra requirement in this way, if we wanted these Riemannian metric tensors to satisfy the monotone invariance property. Okay, so now with these two results, the classical and the quantum one, I would like to pass into the second part of my talk, which, remember, I will try to introduce the algebraic framework of double-set algebras and then try to present you a unified mathematical picture that encompasses Cencov and Petz problems. So in order to introduce this mathematical unified picture, we are going to need mainly three ingredients, okay? So the first one is going to be double-set algebras. So what is a double-set algebra? In order to introduce this notion, we will need to introduce first what is a cis-set algebra. So a cis-set algebra is just an algebraic structure, which is a quintuple, okay? Where this triple is a complex associative algebra. This quadruple is a complex associative involutive algebra, which means that we have added an involution. And finally, this quintuple is an involutive complex panic algebra, where the topological characters come from the fact that we have added a norm, satisfying some suitable compatibility conditions. And finally, if we wanted this algebraic structure to be a cis-set algebra, there is a property, which is a sister property that also needs to be satisfied. Okay? So now, if our cis-set algebra is also the panic dual of another panic space, which is called the pre-dual space, okay, then the cis-set algebra is called a double-set algebra. Okay, So an example of paramount importance of double-set algebras, in fact, abelian double-set algebras, is the algebra of essentially bounded complex valued functions over a measurable space. So this algebra can be endowed with a C-set algebraic structure, but furthermore, it is a double-set algebra because by means of this integration over here, it can be proved that the dual space is isomorphic to the set of mu integrable functions over the measurable space. And in the non-abelian case, the typical example is the algebra of bounded operators, which of course can be endowed with a C-set algebraic structure. And it is a double-set algebra because we can identify the dual space with the space of trace class operators over the Hilbert space. Okay, so now that we have introduced this notion, I would like to introduce the second ingredient, which is which are normal faithful states. Okay, so I hope once we introduce this notion, we will understand why these two ingredients are key ingredients to this unified picture potion, what I call. So in order to introduce what is a faithful normal state, we will need to define the self-adjoint elements of the algebra and the positive elements of the algebra. So since this is a double-set algebra, we not only have a dual space, but also a pre-dual space. And by means of this inclusion of the pre-dual into its double dual, there are some kind of linear functionals that are arising from this pre-dual structure. And these linear functionals are called normal linear functionals. So by means of this inclusion, these normal linear functionals can be classified as positive normal linear functionals, normal states if they are also normalized, and faithful normal states if they satisfy this property over here for this pairing that we have. Okay. So now, in order to give a face to these normal linear functionals and normal states, I would like to discuss a little bit the abelian and non-abelian examples of double-set algebras that we have seen. So in the case of the abelian algebra L infinity, by means of these inclusions, it can actually be proved that the set of all positive normal linear functionals can be identified with a set of positive measures over this measurable space, and that the set of normal states over the algebra can be identified with probability measures which are absolutely continuous with respect to the base measure, which is in this case mu. And in the non-abelian case, this inclusion that is now given in terms of the trace will allow us to prove that the set of all positive normal linear functionals can be identified with positive semi-definite trace class operators on the Hilbert space, and furthermore, that the set of normal states over this double-set algebra can be identified with the density operators of quantum mechanics. Moreover, if we now consider the algebra L infinity, but now over a discrete and measurable space with the counting measure, it can be proved not only that the set of normal states can be identified with the n simplex, but also that the set of faithful states can be identified with a set of strictly positive probability vectors. And now, if we consider now the algebra V of H with H finite dimensional, we are not only going to have that the set of normal states can be identified with quantum states, but also that the set of faithful normal states can be identified with invertible quantum states, or in this finite dimensional setting, with the set of invertible density matrices. So from these two particular examples of double-set algebras, we are arriving into Cencov probability simplex from the abelian side, and into Petz parameter manifold of density matrices from the non-abelian side. Therefore, we can see that double-set algebras and the set of faithful normal states on them are the unifying objects for probability vectors and quantum states. Okay, so now we are in position to introduce the last ingredient of our unified picture potion, which are faithful, normal, and completely positive unital maps. Okay. So if we have a linear map between two double-set algebras, this map is said to be normal if there exists another map, the pre-dual map, which is continuous in the sigma-weak topology and satisfies this extra requirement. Okay? So this map is completely positive if this tensor product, where this is just the identity in the algebra of complex matrices, is positive for all integers n, and is unital if it sends the unit of a double-set algebra into the unit of the other double-set algebra. And the reason why we choose this kind of linear maps is because it can be proved that the pre-dual of an NCPU map actually preserves the set of normal states. Furthermore, if we ask this map to be faithful, in the sense that its pre-dual will preserve also the set of faithful states, then we can arrive to this statement over here. Therefore, in the case when the algebra is the abelian finite dimensional algebra infinity, these maps are going to reduce to faithful Markov maps. And in the case of the algebra being B of H with H finite dimensional, these maps will reduce to faithful CPTP maps. Okay, so therefore, in this algebraic context, will be, let's say, natural to propose that, to ask, let's say, for the invariance or monotone invariance with respect to this kind of linear maps. Okay, so now, if we want to propose an algebraic framework for classical and quantum and information geometry that encompasses Cencov and Petz problems, we will consider finite dimensional double set algebras and the set and the manifold of faithful normal states on them as the unifying objects for probability vectors and quantum states. And instead of considering faithful Markov maps and faithful CPTP maps, we are going to consider the pre-dual map of faithful NCPU maps. And finally, the Cencov-like problem we would like to solve is to determine all families of Riemannian metric tensors on the manifold of faithful normal states of a finite but arbitrary double set algebra, satisfying this monotone invariance property, but now for every map, which is the pre-dual map of a faithful NCPU map. So, when solving this problem, when we studied this problem, we actually realized that Petz classification, once we have overformulated in this algebraic framework, provide us with a family of Riemannian metric tensors that are indeed monotone invariants and whose expression is actually detached from any specific double set algebra. In fact, the expression of these Riemannian metric tensors is given in terms of the inner product of the GNS Hilbert space, okay, related with the state, and also in terms of the modular operator. So the conjecture we are now trying actively to solve is the fact that all Riemannian metric tensors that are monotone invariant are indeed of this form. However, we are now trying to solve or trying to prove the validity of this conjecture in a setting that also includes the infinite dimensional case. When we formulated this problem in here, we were wondering what would happen in the infinite dimensional case, and after some work, we realized that there is indeed a picture that somehow avoids the technical difficulties that appear in the infinite dimensional case. So this picture, which is some kind of a complementary perspective, will need the introduction of a suitable category that we have called the non-commutative probability category, and also a switch from the covariant perspective to the contravariant perspective, but this is for another talk actually. And well, just to finish, once we have found the solution for this problem in this infinite dimensional setting, of course, the solution of this other one will be just a consequence of this one. And well, these are just some of the reference that I would like to highlight for this talk. And well, just to thank you for your attention.
So, there are questions?
First of all, super nice talk. I learned something about this. I guess you mean the positive, your category of positive maps is called usually totally positive.
Sorry, I didn't.
The category of positive maps that you consider, is that the one called usually sometimes totally positive maps?
I don't know if these are totally positive maps, they are just completely positive maps. So I don't know if it's the same thing. I don't know if anyone knows. They are completely positive maps.
Okay, and in the abelian case,
yes,
there is also the Gelfand representation.
Yes.
And I'm wondering if you had considered that in the non-abelian case.
Yeah, we have considered both cases. Actually, This expression that we have in here, we have obtained it considering the non-abelian case, so the Petz problem that we have. And the category we're constructing is a category of double-star algebras, which not need to be abelian or non-abelian or even finite or infinite. So it's for anyone, abelian and non-abelian. So it's a category that is pretty general.
Hi, thank you for your talk. Just by curiosity, I'm asking the category you mentioned at the end regarding the probability. Are there any structure on, like the Markov categories?
Yeah.
Do you start with that point, at that point?
So the category is called the non-commutative probability category. The objects are double-star algebras and are actually pairs, double-star algebras and normal states, okay, which is the notion of a non-commutative probability space. And the morphisms are just completely NCPU maps and the pre-dual of maps, so they are also pairs. And you can prove that this category, you can endow it with garbage and this garbage category, or with a Markov category, by defining the tensor product of double-star algebras, which is actually unique, and that's one of the reasons why we choose double-star algebra, because you have only one good, definitely defined tensor product. So yes, it has much more structure than CP category.
So let's thank again the speaker, and so if you